Hey there, everybody. All right, we've finished chapters 5 and 6. You've taken your midterm, probably. You might have started doing this ahead of time. Here we're going to start chapter 7. We have chapters 7 and 8 for trigonometry left. We're halfway through the semester. Chapter 7 is on working with the identities and stuff like that. It might be a different chapter at your school. This is Math 154. Again, most schools have different numerical numbering sequences for our classes. I wish we had something universal. In fact, we do, at least in California, but the individual schools don't use it. Either way, Math 154, trigonometry, here we go. For what I wanted to share with you, something I have in our Canvas. Let me share it with you. I'm gonna share my screen with you so you can see what I'm looking at. This is our trigonometry class. Let me get back to the base one. Now, this is for summer of 2020. Obviously, future classes will have a different course ID number, like fall and spring and later years. But where I store the information isn't going to change. And why it's not loading, I have no idea. There we go. So we're going to go to Files. Click on Files over here. And important documents. There will be other things in it. This is where I'll have the code for my math lab and things like that. This is something I'm going to use on the first, I'm going to put up real quickly. This is something useful for you. In fact, you might use it for your review for your midterm. I will mention this when I make the video for the midterm review and stuff like that. The first page of it is actually everything we've done in chapters 5 through 6. Well, boiled down. And there are some graphs on the third page that look similar to what we did before. Okay. This page right here starts going over chapters 7 and 8. Okay. But the first page, we're going to start working with identities. So I'm going to put that on the screen. I actually printed it out. I'm going to include it in the lecture notes. I did want to point out something else. There are links to numerous videos over here. GVSU, I think it's Grand Valley State University, Michigan. There's some videos from their class there. Professor Leonard, a lot of girls love him because he looks a little bit like Superman. He's got that build with a little curl coming down sometimes. He's a good teacher. He has videos too. The OChem tutor, this is for organic chemistry, but he does a lot of good math videos. There are other sources for you to check out videos. So please do so while you're going through it. And I will mention this in the orientation if I haven't already. I haven't filmed that yet. So let's get to what we're doing. Let me change what I'm sharing. I want to share my document camera. So my document camera, I printed out the first page. Here it is. Let's call this section 7.1. In fact, I'm going to do 7.1 and 7.2 together because 7.1 is pretty short. I did want to point out some things. This has all your right triangle definitions along with the definitions for, what we do with sine, cosine, tangent. It talks about the unit circle, x and y. We've got a printout of the unit circle with degrees, radians, and the sine and cosine values. Radians, conversions. This is the formulas for circle stuff. In fact, and what we're going to start really working with here, we're doing stuff on identities. So these latter half, or bottom fourth, we're going to use this stuff a lot. We'll see these a lot. You should know tangent and cotangent. I mentioned the odd functions. These apply to their reciprocals as well. So cosecant of negative theta is equal to negative cosecant theta. Cotangent of negative theta is equal to negative cotangent of theta. And secant of negative theta, cosine is the even function. It's the only one that's even here. When you do plug in negative theta, it's the same thing as positive theta. All right. So those are the odd and even functions. Something else I want to point out to you, these are the Pythagorean identities. We covered how to get them, starting with x squared plus y squared equals 1, and making these substitutions in. Okay? The other thing you should be aware of is you will not always see them come in this form. So, like sine squared plus cosine squared equals 1, sometimes we'll just see sine squared. So if you see sine squared theta, you should be able to recall that is the same thing as 1 minus cosine squared theta. At least recall sine squared theta plus cosine squared theta equals 1. Do a little bit of algebra real quick and figure out what it equals. Likewise, if we see cosine squared theta by itself, we're going to want to bring to mind 1 minus sine squared theta. The other two identities kind of do some stuff on themselves. Oftentimes we'll see, here we see secant squared by itself already and cosecant squared by itself already, but sometimes we see tangent squared and cotangent squared. So if you see tangent squared, it's the same thing as secant squared theta minus 1. All I've done is subtracted 1 from both sides. Likewise, on cotangent squared theta, it's cosecant squared theta minus 1. In chapter 7, we will do a lot of manipulation of these formulas, okay? And I'll justify it for you why when we're doing it. Pause and write that stuff down if you will. And then let's get started on the actual chapter. Okay? So, 7.1 is on the trigonometric identities in general, and we expand upon it. Identities, I've used this word before, identity. I don't know that I've ever actually told you what it means. Identities are rules or formulas that hold true for every value in their domain. And the domain is all input values that work, that yield results. In algebra, this was our x values, and y values were our output or the range. Same here. So identities hold true for every value in the domain. And here we're going to be using theta. We're going to use 0 to 2 pi. Those are the ones we really care about. We really care about the least positive ones. Care about this range. In general, negative infinity to infinity is usually all numbers work. Okay. So what we're going to do is we're going to start off with if tangent theta is equal to negative 5/3, where theta is in quadrant 4. Quadrant 4. Find the other 5 trig functions. Using identities. Okay. So the way we're going to tackle this, what equations do we have that have tangent in them that might yield other things? Let's hit up, well, cotangent theta just spits itself right out, doesn't it? Cotangent theta, we're going to use the reciprocal identity. 1 over tangent theta. which really just flips this over, so it's negative 3/5. Bam, one of them's done already. Now we need sine theta, cosine theta, cosecant theta, and secant theta. So I'm just gonna put them down, remind myself what I'm looking for as I'm going. What other functions do I have here that might work? Well, I've got tan theta is sine over cosine. If I plug it in now, I've only got one. Having one out of three things isn't all that helpful. And cotangent's the same thing. I've got cosine over sine, not helpful yet. So maybe let's use one of these identities. We've got tangent squared plus 1 is secant squared, or we could work with cotangent. Let's work with tangent. So I've got tangent squared theta plus 1 equals secant squared theta. We'll plug in negative 5/3 and square it. Negative 5 squared is 25, 3 squared is 9. If I want to add the 1 to it, I need to get a common denominator. And when it's 1, you just put it over the denominator you need with the same thing on top. And if I add those together, I get 34 over 9, right? So if I take the square root of that, square root of 34 over the square root of 9 is 3. Which one do I need? Let's just take a quick look at quadrant 4. We've got some angle here like this. Theta hat's right there, our reference angle. All strippers take cash. Cosine and secant are positive here. So cosine's greater than 0, secant's greater than 0. We want the positive one. Okay. And that one's good right there. We flip it. So I got it. Let me fill it in. Root 34 over 3. If I want cosine theta, flip it. Flip it real good. And we want to rationalize it. We'll multiply top and bottom by 3 over, or root 34 over root 34. Oops. And we don't have the radical on bottom anymore. So cosine theta is 3 root 34 over 34. All right. Now what? We need sine and cosecant. So we've got some options for sine. What might be easy, we can use any of these formulas, but if we look at tangent theta, let's look at tangent theta. Because we could work with this 1 plus cotangent squared theta and equals cosecant squared theta. We could do that. But let's be smart about it. It will get us the same result, I promise you. It'll get us the same result. But let's go with tangent theta equals sine theta over cosine theta. Isn't that really, I could write this as sine theta times 1 over cosine theta if I wanted to. So tangent theta is sine theta times secant theta. All right. Well, tangent theta is negative 5/3 equals sine theta. We need that. Secant theta is root 34 over 3. Well, if I isolate sine theta, multiply both sides by 3 over root 34, I get sine theta. That clears. 3's cancel over here. I get negative 5 over root 34. And if I rationalize, I get negative 5 root 34 over 34. All right. Let's put that in up here. Does that make sense? Sine is negative in quadrant 4. That works. And if we want cosecant, I don't really want to flip that one. I want to flip this one. Because if I flip this one right here, then I have a radical on top right away, and I don't need to rationalize it. Negative root 34 over 5. Now, if you go through, you could also use, I'll put this here, or do 1 plus cotangent squared theta equals cosecant squared theta. And 1 plus cotangent squared, we got that right here. 1 plus negative 3/5 squared equals cosecant squared theta. Go through it. You got 25 over 25 plus 9 over 25 equals cosecant squared theta. And we can see how that gets us there, right there. I need a new green pen now. And that one's not working either. There we go. I see a lot of ink in this one. If I can get it to come out, there we go. 25 over 25. God, this pen don't like it either. So there's a couple ways to skin that cat. If you have cats or lost a cat recently, sorry, it's just an expression my mom uses. I don't have anything against cats. I don't hurt cats. Well, I do have, I don't want a cat for myself. I like my pets to worship the ground I walk on. My dog Astro, I've shown a picture of him in our orientation video. He worships the ground I walk on. Cats are like, feed me and get the hell out of my face. Not for me. All right. Let's take a look at another type of problem we'll run into. Another thing we'll see if I can get green to work now. Write sine x in terms of cotangent x only. So I'm going to pull out my formulas, take a look at them. What do we got here? Maybe I should just keep these up right here for a little while. What do we got going on here? So I need sine x and cotangent x. What do I got? Well, I've got sine x equals 1 over cosecant x. And I got nothing else with sine there. This looks like it's going to take me further away. Tangent theta, cosine theta. Cotangent here has got cosine and sine. I don't have cosine though. Maybe use that. That starts heading in the right direction, it looks like, maybe. Sine squared theta equals 1 minus cosine squared theta. That looks similar to something like this. I could maybe use the cosine squared theta. I don't know. Let's see what else we got. Well, let's write it down while we're looking at it. We got sine squared theta plus 1 or cosine squared theta equals 1. And for this one, we've got the cotangent squared. 1 plus cotangent squared. Well, we're doing x, so maybe I should shift back to x. Cosecant squared x. I like this. Look at this. Look at this. I got cosecant x in both of these. And the only thing I have left in those that is the sine x and cotangent. And those are the two things I'm going to work with. So it looks like there's a bridge here. Let's use these. This is going to take the equations. Okay. So what can I do? Well, I want sine squared, or I want sine. So let's take this one and flip it over. Let's do the reciprocal. 1 over 1 plus cotangent squared x equals 1 over cosecant squared x. And that one on the right is sine squared x. Okay. I don't even need, yeah. I don't even need that one other than I used it to flip it. That's how it comes in. Because this is 1 over cosecant x squared, which is sine x squared. There we go. That kind of illustrates it a little bit better. And now that we have that, I can just take the square root of both sides, right? Sine x equals plus or minus the square root of 1, which is 1, over the square root of 1 plus cotangent squared. And I should probably rationalize it. So we'll multiply top and bottom by that radical. And ta-da! I have sine x written in terms of only the cotangent function. Yes, there's some other numbers, there's some radical signs in there, but it's the only trig function in there. Now, if you're a little confused about how I did this reciprocal thing, the reciprocal idea, I'll write it out a little bit slower. This always works. I had 1 plus cotangent squared x equals cosecant squared x. The idea of doing the reciprocal is to divide both sides by cosecant squared x times 1 plus cotangent squared x. Just everything that's on top. And on the left side, the 1 plus cotangent squared cancels out, and we get 1 over cosecant squared. And on the right side, the cosecant squared cancels out, and we get the 1 over 1 plus cotangent squared. Now, this one never equals 0. Anything squared is always greater than 0. We add 1 to, or 0. We add 1 to it, it's always positive. The assumption by doing this is cosecant squared x does not equal 0, which means cosecant x does not equal 0. Which means 1 over sine x does not equal 0. And this cannot equal 0. There's no way this can equal 0. This could be undefined, but cosecant x never equals 0. In fact, if we, let me bring that back up real quick. Let me change what I'm sharing. This is from the file we were just looking at. We come down and look at the graphs. Cosecant x is right here. It never touches the x-axis, which means it never equals 0. Bam. So we can divide both sides by it, and it doesn't change anything. All right. Let's bring our document camera back up. That's the principle behind doing what we did. Okay. Show must go on. Let's do some more. Let's rewrite using sine and cosine the following. I please simplify and leave no fractions. And what we're going to have, what we're doing is we're going to start with secant squared theta minus 1 over cosecant squared theta minus 1. Okay. The reason why we have you do this a lot in 7.1 and throughout chapter 7 is when you get to calculus, you were going to be doing a lot of things called derivatives and integrals. That's the heart and soul of calculus. A lot of what we do. And a lot of times trigonometric functions pop up in there. In fact, often crappy looking ones like this show up. If you find a way that you can write it in a simpler form that has a easier derivative or easier integral, it can make doing the work a lot easier, which requires being able to manipulate these functions or equations or trigonometric expressions. So let's rewrite this. What is secant squared? Secant squared is 1 over cosine squared. And cosecant squared is 1 over sine squared theta. What I'm going to do is I'm going to get a common denominator on top and bottom. 1 over cosine squared theta minus cosine squared theta over cosine squared theta. On bottom, I've got 1 over sine squared theta minus sine squared theta over sine squared theta. And now I'm going to put them together, top and bottom separately. This gets me 1 minus cosine squared theta over cosine squared theta times 1 minus sine squared theta over sine squared theta. We still have fractions. We don't want them. But look at this. Does that look familiar? When we see cosine squared theta and a 1, always check your Pythagorean identity. Does it simplify? Yes, it does. 1 minus cosine squared theta equals sine squared theta. So I can write this as sine squared theta over cosine squared theta. And the same thing with the 1 minus sine squared theta. It equals cosine squared theta. Well, isn't that the thing on top, tangent squared theta? And the thing on bottom, cosine squared theta? Or cotangent squared theta, I should say. And cotangent squared theta, it's still a fraction. I don't want it. This is tangent squared theta times 1 minus, or times 1 over cotangent squared theta. But we've got a trig identity for that. Tangent theta equals 1 over cotangent theta. And that is tangent in there. And now we've got tangent squared and tangent squared. This all wraps up into a nice tangent to the 4th power of theta. So I bet you didn't know when you started that secant squared theta minus 1 over cosecant squared theta minus 1 was going to simplify into something so simple. That's why we do it. Sometimes you start off with something crappy, you can end up with something simple. Okay, this is huge in calculus. You'll see. Presumably, if you're taking trigonometry, you're going on to calculus. I can't imagine why you would take trigonometry and stop. Unless it's a hobby. Some people have hobbies. If math is your hobby, I would consider, and it's not any related to your major, I would urge you to look at calculus and physics and things like that. Good stuff. Is this the only way to do this? No. Let's try to do this another way. Let's do this another way. Let's start with this and do it another way. So I'll rewrite it. What else do we have here that's got these things? I immediately shifted to sine and cosine. But if I look at my equations, I've got a secant squared, don't I? It's tangent squared plus 1. So I'll replace secant squared theta with tangent squared theta plus 1. And I still have the minus 1 there. Cosecant squared theta is 1 plus cotangent squared theta. And I still have the minus 1. And look, 1 minus 1 is 0. So this top just simplifies to tangent squared theta. And I got 1 minus 1 down here. That just gets us to cotangent squared theta. And that really jumps us way past all this work we did here. Going to cosine and sine and doing all this. I'm over here in a lot shorter of a step. You see that? We switch to cosine and sine. These are good manipulation techniques. Sometimes this is what you got to do. Sometimes there's a shorter road. So sometimes just stopping and looking at your options might make things go quicker. And we just showed that that equaled tangent to the 4th power of theta. Okay? So we can work smarter, not harder. Smarter is better. We want to work harder. Go do manual labor or something. That's harder, right? That's the idea of what's going on in chapter 7.1. 7.2 goes a little bit further. 7.2, we look at verifying identities. And what this means is we've got this. We've got side A equals side B. And there's trig functions in both. There's stuff in both sides. How can I prove that the left-hand side which I am going to call LHS for this lecture, because I say it a lot, equals the right-hand side. Which is RHS. I'm going to use that. Just like I said in the last one, with 7.1, this skill is super duper important. Super duper. Ooper. Super duper important in calculus. What we're effectively doing is algebraic manipulation with trig functions. With trig functions. The trig functions, algebraic manipulation with trig functions, which show up in derivatives and integrals all the time. Well, not all, but often enough. All right. And something that I didn't understand why when I was a student, why they had me doing it, because it wasn't really explained to me that this was, we were aiming for what we use it for in calculus. We only want to manipulate one side to make it look like the other. At least in the final answer. And you may ask why. Can I tinker around with left-hand side, right-hand side, as long as they end up looking the same? Isn't that what matters? No. The reason why is we generally only start off with one side. With just an expression, not an equation. We want to convert it to a simpler form for calculus. Usually for calculus. How about we add that? So that's a lot of writing there. It's just the reasoning of what we're doing. When we actually do it, it's not too bad. Okay. Pause it if you need it up longer, and we're going to get started. So there's an expression that's often used, know thyself. If you know stuff about yourself, how you are and what you're the way you're acting, less stuff will surprise you, stuff like that. In terms of math, know thy identities. These are David's pro tips. For verifying identities. And the first one is know them. Know thy identities. So that's pro tip number one. Be comfortable with the identities. And be aware of the alternate forms. And we mentioned this just a little bit ago. For example, we've got cosine squared theta plus sine squared theta equals 1. But alternate forms are cosine squared theta equals 1 minus sine squared theta. We can have sine squared theta equals 1 minus cosine squared theta. Hell, we can even just change the order. It's all the same thing. These are all just the same equation written in different forms. Another thing to do while you're verifying these identities, work with the more complicated side. Try to simplify it to make it look like the simpler, or try to make it look like the simpler side. And the reason why is oftentimes complicated side, you can spot stuff that leads to simple stuff. Is easier to recognize where it appears in identities. If you start with the simple side though, starting off with sine theta, there's a lot of ways we can go to any other thing in those. Like, look at this. If I start off with sine theta, how many things here have sine theta in them? That one does, that one does, that one does. The odd functions do. This one does. They show up all sorts of the place. If I start off with 1 minus cosine squared theta, well, that only shows up in one spot. Start with the more complicated thing. If all else fails, well, not all else. This is always or usually a useful thing. Express the trig functions using sine and cosine. We've already seen that secant and cosecant can be written in terms of sine and cosine, but we also know that tangent and cotangent can. If we get them all down to sine and cosine, we've only got two different trig functions, and sometimes it's easier to work with. This is really a subset of number 1. I said know thy identities. Know thy algebra identities. Or algebraic identities. And you're like, what the hell are those? You've seen them. A plus B squared. This is A squared plus 2AB plus B squared. If we look at A squared or A minus B squared, same thing, it just changes the middle sign. Speaking of which, when it's on the outside, or the square is on the inside, A squared minus B squared, that's the difference of squares. And then we've got A cubed minus B cubed. And it's very similar to A cubed plus B cubed. These are the cubic ones. They always have, to start off with, we have A and B, and they use the same size that it starts with. Then it has an A squared, AB plus B squared in both of them, multiplied times the first parentheses. And whatever sign was here is here, and you use the opposite one here. And it works on both. Plus here, minus there. Handy way to remember it is the complicated side only has one negative sign. So let's take a look at how this might apply to our trigonometry. I can pause it for a second, let you take a pick. It lasts longer. Or better yet, take notes. Then it goes through your brain, through your eyes, through your brain, out your pencil. More processing than taking pics. If you show up to college classes and thinking taking pictures of the board is the same thing as writing lecture notes by hand, you are making a very, very bad mistake. You're going to make it much harder to learn your stuff. Any class, not just math. Take notes. In fact, I tried doing that in grad school myself. If it got going too quickly, I would take pictures. I always leave room to write down the notes in the notes and take it and fill in my notes later on from the pictures. I found the times when I took pictures and didn't have any intent, like I just took a picture, very rarely did I go back to it. So I found I just needed to learn how to write faster, or deliberately force myself to go back and do the notes because I didn't learn it. If I just take a picture, I very rarely checked it. Let's do some examples with that algebra idea. I've got 1 minus 2 cosine squared x plus cosine squared, or cosine to the 4th power of x. I've got something to 1 power here that's double the power here. Okay, I'm going to say, well, what if we make b equal cosine squared x? And let's make a equal 1. So I've got a, which is 1, minus 2b plus b squared. Now I'm really close to one of those algebra identities. A squared minus 2ab plus b squared was a minus b squared, right? Well, isn't a just 1? Can't I multiply a by a and not change it since it's 1? And multiply 2b by a and have it be the same? That would be the same if I use those. So these two are the same. This is what I want. I want a minus b, that power thing squared. I got a minus b is 1 minus cosine squared x squared. Well, that simplifies it some, but guess what? This simplifies even further. What is that? Sine squared, right? Which means this all simplifies down to sine to the 4th power of x. If you don't recognize it right there, you could actually, so I've seen this done. Rather than that, replace the 1 using sine squared plus cosine squared equals 1. So I'll just replace the 1 in red. I guess it's x, so I better put x back in. Those are what I'm replacing. I still have the minus cosine squared x squared. And now cosine squared x minus cosine squared x is just sine squared x. And we got the square on the outside. That's the less likely route to do it, but sometimes people do it. What was the last one I did? Last one was number 4. Let's take a look at number 5. Number 5. So when I taught pre-algebra and algebra, this is the common thing I said. Fuck fractions, all right? Hell with fractions. Get rid of them if you can. Or simplify by using an LCD. For example, if I have 1 over sine theta plus 1 over cosine, I don't want sine squared, plus 1 over cosine theta. The idea of this is the LCD, just take the other fraction and multiply top and bottom by it. So the other fraction had cosine theta. I'm going to multiply sine theta by that. And the other fraction for cosine theta is sine theta. We'll use that. And now we have an LCD of sine theta, cosine theta. And on top, we have cosine theta plus sine theta. Sometimes that helps. This case, it doesn't do a whole lot, but that's the idea of LCD. Pause for a second. Are you ready for more? All right. Number 6. Know what your target is. Or what are you trying to get to? You know, if you're working the left-hand side of the equation, it's generally the other side of the equation is what you're trying to get to. It already has its own trig functions in it. Use the other side to guide your choices. So, for example, I start off with cotangent squared theta plus 1 equals 1 over sine squared theta. Well, for me, the simpler side is the right-hand side. So I'm going to work the left-hand side. I'm aiming for sine theta in it. Okay. So when I look at my identities, I wouldn't look at them. I have them memorized, but you may not at first. Hopefully you get there. Actually, the only one I have really memorized is this one. Sine squared theta plus cosine squared theta equals 1. That is the only one I have memorized. I know how to get the other ones, dividing by sine theta or cosine theta. So when I see cotangent squared or secant squared, tangent squared or cosecant squared, I quickly go through the formula real quick and do it. I'm looking for sine. So which things up here have sine and sine only? I've got cotangent theta here. It's got cosine theta and sine theta. It's got sine theta. It might work. It might work. That's got cotangent, but it's got tangent. I don't want to go that route. And I got this one. In fact, this one's got 1 plus cotangent squared in it already, and it goes to cosecant, and I know cosecant goes to sine. So that's a good choice. Options I had for cotangent. Let me just write them down. Cotangent theta equals cosine theta over sine theta. Or we could use cotangent squared theta plus 1 equals cosecant squared theta. Do both of them work? This one looks like it's the quicker route. I'm going to do that one first, but I'll show you B as well. A. I'm going to replace cotangent squared theta plus 1. I'm going to replace that with cosecant squared theta. That's my substitution. And the right-hand side goes untouched, 1 over sine squared. And then I manipulate the cosecant squared theta. This is cosecant theta squared, like that, which equals 1 over sine theta squared, which equals 1 over sine squared theta. Bam. So that was option A. Can I get there with B? So I've got cotangent squared theta plus 1. And goal, 1 over sine squared theta. That's my goal. I'm going to use cosine theta and sine theta. And it's squared, so each of these is squared, plus 1. Now I've got sine squared theta. What did we say about fractions? To hell with fractions. Getting rid of them here doesn't help. Maybe get an LCD. Cosine squared theta plus sine squared theta over sine squared theta. That's by treating the 1 as sine squared theta over sine squared theta. And that actually works. The top is an identity. Cosine squared theta plus sine squared theta equals 1. That works. So there's a couple routes to get there. All right, idea number 7. I'll pause it for a second. Idea number 7 is use trig conjugates to simplify denominators. Now remember complex numbers, complex conjugates. If I had 1 over 1 plus I, the conjugate of 1 plus I is 1 minus I. So the conjugate of 1 plus I. Let's do a trig version of that. So for our example, we'll have, let's start off with 1 over 1 minus cosine x. If I do something similar where I treat that, just change the sign, this will be 1 plus cosine x. And we're multiplying the whole thing on the bottom by the whole thing on the top. The top is just 1 plus cosine x. This is like a minus b times a plus b. That's where our algebraic identities come in. It's a squared minus b squared, where a is 1 and b is cosine x. So a squared minus b squared would be 1 minus cosine squared x. And we can simplify that. The bottom is sine x, or sine squared x. Now you may see something different than 1 minus cosine x. If you have like a minus a cosine x, or a plus a sine x kind of thing, factor out the a. Okay. And this idea also works well if we've got a secant x on bottom plus or minus 1, or cosecant x plus or minus 1. In fact, this a minus a over x is a minus or plus, and we do having the sine x or cosine x as the latter half, or the secant x, cosecant x as the first half, with a plus or minus 1, gets you to those other Pythagorean identities that we have up here. Okay? All right. So those are your options. Let's try some examples. Ready to get started? Let's do it. So project number one, assignment number one, prove or verify problem one, secant squared x cosecant squared x equals secant squared x plus cosecant squared x. That's deep. Multiplication turns into plus? Going to addition? That's deep, dude. That is some seriously deep stuff. In trig, there are times where it works. Now, I think the left-hand side is more complicated. LH side is more complicated. Let's use that. Because the multiplication is harder to deal with than the addition. So I'm going to write this as, well, let's use the identities we have. Secant squared is tangent squared plus 1. And cosecant squared x is 1 plus cotangent squared. And it still equals the right-hand side. All right. Let's distribute. So I've got tangent squared x here, and then I've got tangent squared times cotangent squared. And then the latter one, I've got 1 times 1 is plus 1, and 1 times cotangent squared is cotangent squared x. And at this point, I'm just going to write equals, and I'll just leave RHS. That way I don't need to keep writing the longer or the other side out. Well, what do we got here? What's this? What is this going on? What's going on right here? That one looks kind of messy. So I'm going to fiddle with that. Let's see what goes on there. Let's turn it to sines and cosines. I got plus sine squared x over cosine squared x. And cotangent is cosine squared x over sine squared x. Wow, that just cancels out, doesn't it? Cosine squared, they leave behind a 1. Sine squared, they cancel out, leave behind a 1. This turns into tangent squared x plus 1. And then I still have plus 1 plus cotangent squared x. And we're still aiming for the right-hand side. All I've done is manipulate the left. And I go, okay, I've seen this. I've seen this, and I've seen this. I'm getting there. Let's bring that plus sign down in the middle, bring it down. What's tangent squared x plus 1? Secant squared, we use the identity up above. Well, for me to bring that plus down, I gotta treat it like that. And 1 plus cotangent squared is cosecant squared x. And the right-hand side, I'm going to write it down again because that's what it was. I got where I was going. Ta-da! Proven. You will see math teachers and people that are like deep into math. Proven, they also say QED. It's Latin for some, I don't know. Latin for I proved it. All right, really, that's what it is. It's Latin for I proved it. Do we have to use the left-hand side? No, we don't. Let's do the same proof using the right-hand side. So I'm going to rewrite this down. And now I'm going to work the right-hand side. So LHS equals secant squared is 1 over cosine squared. And cosecant squared is 1 over sine squared x. So I just shifted to sines and cosines. Now I've got different denominators. Let's get an LCD. That might help. I need to multiply cosine squared x by sine squared x. So I'll have sine squared x, cosine squared x, sine squared x. And then I multiply this one by cosine squared x over cosine squared x. And combine the fractions. Top is an identity. And this is still the left-hand side. I haven't touched it. The top, sine squared x plus cosine squared x is 1. And I can write this as 1 times cosine squared x times 1 over sine squared x. I'm just breaking up the fraction. And finally, we use our reciprocal identities. Cosine squared x is secant squared x. And sine squared x is cosecant squared x. And that's my left-hand side, right? Now, I'm writing it on the right here, but that was the left-hand side. QED. Which way you think is easier is entirely up to you. Is that the only way to do it? Now, I want to show you, you have options. Let's do it another way. And not what, Mr. Jones, are you on crack? No. No. Secant squared x, cosecant squared x equals secant squared x plus cosecant squared x. All right, I'm going to work with the left-hand side, but we're going to do something different. I'm just going to do a partial change. Let's just change cosecant squared x. This is 1 plus cotangent squared x. And that equals our right-hand side. And if I distribute, I got secant squared x plus secant squared x cotangent squared x equals, I'm going to write it out just to point out something. I've got secant squared x on both sides. I'm trying to make that look like that now. So that's the one I got to work with, really. That must be cosecant squared x. Is it? Let's tinker with it some more. So I still got my secant squared x. Maybe this is where we start throwing in our switch to sines and cosines. So secant squared is 1 over cosine squared. And cotangent squared is cosecant squared over sine squared. And that equals right-hand side. And it looks like cosine squareds cancel out, leaving behind a 1. Secant squared x plus 1 over sine squared x. And finally, we use the reciprocal identity. Again, QED. Different proof. Deep, huh? Ready for another? All right. I'll do a fresh page for each one I do because sometimes these take a little while. So prove, verify. We've got secant theta plus cosecant theta times cosine theta minus sine theta equals cotangent theta minus tangent theta. Well, the right-hand side definitely looks simpler, so let's work the left. It's the complicated side. First thing, distribute. Secant theta, cosine theta, and then minus secant theta, sine theta, and then plus cosecant theta, cosine theta, and then minus cosecant theta, sine theta. And that equals the right-hand side. We're only working one side here. At this point, I got too much things going on. Let's go to cosine and sine. So what's changing here? This is staying the same. This will stay the same. That'll stay the same. That'll stay the same. And I'll sub in the other ones using green. Secant theta is 1 over cosine theta. 1 over cosine theta. 1 over sine theta. 1 over sine theta. All right. Now we multiply. This is really cosine theta over 1, and these are all, I can write them as all over 1 to do fractional multiplication. These just cancel out, right? We just get 1 there. Here I have sine theta over cosine theta. Here I've got cosine theta over sine theta. And the sine thetas cancel out. I got a minus sign now. This is minus 1. Well, 1 and minus 1 cancel out, right? Let's write these using the quotient identities. This is negative tangent theta plus cotangent theta equals, and look at that. All we have left to do is just change the order, right? We got to keep the signs with our things. The minus goes with the tangent. Cotangent's positive. We switch the order. Cotangent theta minus tangent theta equals the right-hand side, QED. I like to just put a check mark on it when I'm done. That's my thing. I use check marks. Ready for another fun one? They're all fun. Hopefully you tried to pause that last one and do it yourself. Try to pause it and do this one yourself. Prove or verify. I've got sine squared of negative theta plus tangent squared of negative theta plus cosine squared of negative theta equals secant squared theta. Try to prove that. All right, I'll assume you paused it. This looks like we can take advantage of the odd functionality. We're having negative things in there. But the square thing's thrown it off. Let's move the square outside first. This is really sine of negative theta, that's squared. And this is tangent of negative theta, and that's squared. And this is cosine of negative theta, and that's squared. All right. So using the odd functionality, this is negative sine theta squared. This is negative tangent theta squared. And cosine is an even function. Cosine negative theta is the same. Oh, I don't even, I'm on the screen. I'm using these functions right here, the odd and even. Cosine negative theta is cosine theta. And I guess I should put these in parentheses. Equals secant squared theta. Keep your eyes on the prize. So what do we have? This is sine squared plus tangent squared. The negative times the negative is a positive. Right side still secant squared theta. Now what can we do? What do we have that has these things in it? Well, we have the Pythagorean identity, right? Sine squared plus cosine squared equals 1. That equals 1. And I still got tangent squared theta. We have a right-hand side is secant squared theta. We're almost done, right? This is the other part of the Pythagorean identity. We've got that one right there. Secant squared theta equals secant squared theta. QED or check mark. What if we had worked the right-hand side? So here I work to the left. I'm going to show what happens when you work the right. What happens working the right? So I start off with secant squared x, or secant squared theta. And I know that equals 1 plus tangent squared theta. Apparently, if I look at this one going backwards, I need to write this 1 as sine squared theta plus cosine squared theta, and then plus tangent squared theta. And then I need to recognize that this is sine theta squared like that, cosine theta squared like that, tangent theta squared like that. And then I need to be able to recognize that this is the same thing if I make it negative inside. Let's see, how do I put this here? I can treat sine squared as, apparently I need to have a negative in there. Negative sine theta times negative sine theta will give me sine squared theta, right? And then I can make the jump that this is sine of negative theta squared plus cosine of negative theta squared plus tangent. Since it's an even function, negative theta squared. Oh, not that one. This one needs to be a negative. So we got a negative, 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 negative on the inside. And finally, I end up with cosecant squared negative theta plus secant squared negative theta plus tangent squared negative theta. Now, the reason why I did that is this was working the simpler side. The only step that was easy or even intuitive was secant squared theta equals 1 plus tangent squared theta. All of those other steps are serious jumps in logic and reasoning to get to where you're going that most people can't do, myself included. It's too big of a jump. Going the other way, though, I just used identities that we had, little formulas that we had. Starting on the left, going to the right, I just used things we had up here in the identities to start changing stuff. Here, I did the same thing, but realizing I could go from 1 to sine squared theta plus cosine squared theta, especially with all of these functions up here that have 1s in them. What? 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 No. No. Not going to happen. Okay, so far, we've only worked one side. This is how you have to do it in calculus. But the trig things like to give you fun stuff. Sometimes working both sides can help you make jumps in reasoning. especially if they're both crappy. Both sides suck. All right. One plus sine theta, here's my example. 1 plus sine theta over 1 minus sine theta minus 1 minus sine theta over 1 plus sine theta equals 4 tangent theta secant theta. All right. So both sides are kind of crappy. The left side's got fractions with different denominators. Right side's got some weird shit going on. First intuitive step. Let's try to, we've got a 1 minus sine theta, 1 plus sine theta. Let's get rid of that by using the reciprocal or the conjugates. So we'll multiply by 1 plus sine theta on the first one. And I guess I should leave myself a little bit more room. I'll put a minus there. And I'll put this right here. 1 minus sine theta over 1 minus sine theta. And remember, this is in parentheses, so it's got to multiply to everything. So over here, I've got 1 plus sine theta squared. And on bottom, I've got 1 minus sine squared theta. And I'm going to have that on both, right? So I'm going to just combine them now. Both have the 1 minus sign. The denominators are the same. This minus sign comes down. I've got 1 minus sine theta, and that's squared. I got a lot of signs here. There's no signs over here. Let's make it look like a sign. Let's get to sines and cosines. So I've got 4 sine theta cosine theta times 1 over cosine theta. And now, what can we do? Maybe distribute. Distribute on the left. So I've got 1. This is the algebra stuff. So we've got 1 plus 2 sine theta plus sine squared theta. And I'm going to say minus. I'm going to leave this all in parentheses because that minus is in everything. 1 minus 2 sine theta plus sine squared theta. The bottom we have an identity for. That's cosine squared theta. If I continue working the right side, I've got 4 times sine theta over cosine squared theta. Looks like my bottoms match. In fact, let me put that 4 up here. Apparently the tops have to match. So let's see what happens if I clean it up. So I distribute. That makes this minus 1 plus 2 sine theta minus sine squared theta. And now I can combine like terms. 1 minus 1 go away. 2 sine theta plus, I'll put them together. I'm going to put similar terms together just so you can see what I'm doing. And then I've got plus sine squared theta minus sine squared theta over cosine squared theta. And then it's a little bit easier to see what cancels. 1 minus 1 goes away. 2 sine theta plus 2 sine theta is 4 sine theta. And then we've got cosine squared theta on the bottom, and the sine squareds cancel out. Okay. And we've got it done. Other teachers, and I'm going to show this, many teachers will want you to continue working the left side one of the sides, in this case, the left side, because it's more difficult to get the other. So we'll do that. At this point, I've got 4 sine theta on the left, cosine squared theta. I'm going to replace the right-hand side with what I started with, 4 tangent theta secant theta. So this is a continuation. Putting right-hand side back in. At this point, you break it up into 4 times sine theta over cosine theta times 1 over cosine theta equals right-hand side. And then finally, you use the quotient identity, reciprocal identities. Bam, QED, done. That's the way I had to do it when I learned it. And I didn't know why. I thought it was silly when I got both sides to equal the end or something that matched. I thought it was done. I didn't understand we were doing something for calculus. You should try to do it that way though. All right. One more. One more. Uno más. Uno más. You try. 1 minus cosine x over 1 plus cosine x equals 2 cosecant squared x minus 2 cosecant x cotangent x minus 1. I'm going to pause it, let you work it. All right, assuming you did. Maybe use the conjugate. So I'll multiply this by 1 minus cosine x. The bottom is the difference of squares. It turns into 1 minus cosine squared x. That's why we did it. The top is 1 minus 2 cosine x plus cosine squared x. And right-hand side still here. Bottom is sine squared, right? Still equals the right-hand side. And this I can turn into, well, let me rewrite it like this. I've got 1 minus 2 cosine x plus cosine squared x. That's times 1 over sine squared x. That way it's a little bit clearer to see what the jump is. That's cosecant squared x, right? So we're trying to get to here. Maybe we should work that a little bit. Two over sine squared x minus 2 I've got 1 over sine x, cosine x over sine x minus 1. Which is 2 sine squared x minus 2 cosine x over sine squared x minus 1. Maybe let's get a common denominator, sine squared x. Which means this right-hand side is 2 minus 2 cosine x minus sine squared x over sine squared x. That helps me actually quite a bit. I've got the minus 2 cosine x, and I've got a relationship between cosine squared x and sine squared x. Maybe should put this is cosecant squared x, right? That one leads to that, leads to that. I just need to get this sine squared x and part of this 2 to change. Let's change this. 1 minus 2 cosine x. Cosine squared x is 1 minus sine squared x. So that's the replacement I'm making. And that equals the right-hand side. So I had to work the right-hand side to help steer me where I'm going. I can put the ones together. Now I've got 2 minus 2 cosine x minus sine squared x. And I'm going to put the cosine squared x back on the bottom as secant sine squared x equals the right-hand side. And we break this up. Break up the fraction. This is 2 over sine squared x is 2 cosecant squared x. This is minus 2 cosine x over sine x times 1 over sine x. I'm splitting up this one a little bit. And this last one is just minus 1 equals right-hand side. And finally, 2 cosine squared x minus 2 cotangent x cosecant x minus 1 equals, that equals the right-hand side. Done. QED. So here I kept going the full way. I probably would have stopped right here. I would have wrote sine squared x as 1 minus cosine squared x, got it to look like that, and stopped. I'm trying to show you how the correct way of doing it is just working one side. Sometimes you work the other side on a piece of scratch paper to help steer you where you're going. That wraps up 7.1 and 7.2. Peace. I'll catch you later. Let's end this for you. End this charade.